Hello everyone. So I hope you guys are doing well during the lockdown, and I hope that this will become better soon. Okay, so in today's video, I'm going to show you one method to increase the measurement capability of etracer to 600 milliamp. That's doubling the original design spec of 300 milliamp. Okay, so I wrote this document for presentation, and probably rewrite this document and put it on my website. So the maximum current measurement capability of etracer is designed to be 300 bit. It's a compromise of resolution, noise, hardware complexity, all that kind of stuff. So this capabilities is actually more than adequate for testing and tracing most common audio tubes like 300B, KT88, or 6550. And but for some tubes, we do need this. We do want a higher current measurement capability for tubes like 6C, 3C, or the latest KT150. So this application note describes the method needed to modify the modification needed to modify the PCB to support the increase in current measurements capability to 600 milliamp. Okay, so before we start the talking about the discussion, we need to look at the side effect. So the immediate side effect of such modification is we're going to lose 1 bit of resolution in the ADC. And here are some maths, like very basic maths. The maximum current measurement capability is 300 milliamp. With a 14-bit ADC, and we have a PGA programmable gain amplifier. It's configured at 2x, so the ADC resolution is about 10 microamp. And we, in the software and the firmware, we also use averaging technique to increase the theoretical resolution. But theoretically, for this method, the averaging method only works with AWGN background noise. AWGN stands for additive white Gaussian noise. But in reality, this is not always true. So the boost in resolution is not cannot be very high. Okay. So although this resolution is more than enough for testing tubes with current readings in the milliamp or a fraction of milliamp range, it's very marginal for heater cassette leakage current measurement. So if you remember, in the software for heater cassette leakage measurement, we have a pass-fail threshold instead of a measurement, because the measurement cannot be the precision is not enough for a precise reading. So we have a threshold of 10 microamp or 20 microamp as a pass criteria. So if we modify the etracer hardware to support a maximum of 600 milliamp, so we are going to lose 1 bit of resolution. So effectively increase the ADC resolution from 10 microamp to about 20 microamp. So this might render the heater cassette test useless. So this is many users feedbacks. They don't use the HC test much. So this is a trade-off you need to consider. The second problem or second side effect is the noise floor. So we because we increase the current measurement capability to 2x, the noise floor is effectively doubled. A third side effect is we are going to lose the voltage accuracy when the HV2 current is high. So we'll see this problem more in detail when we start when I show you the calibration. So this is not so here is some background of this problem. During the current measurement cycle, the boosting circuit on the etracer PCB is turned off to minimize the background noise. So the device under test is solely powered, connected to the blue 45 microfarad NKP capacitors. So it's inevitable that the voltage on the capacitor will drop gradually when it is discharged through the device under test. So the higher the discharging current, the bigger the voltage drop. So this phenomenon is usually not a problem for HV1 because every time we at the end of every current measurement, we'll compensate. We'll read the voltage on the capacitor again and compensate the voltage drop. But however, for HV2, the story can be different. It depends on the test the configuration of the DUT. So, for example, if this DUT is connected as a pentode and HV2 is connected to the screen electrode of the DUT. So for pentode, we want the voltage applied to the screen electrode to be as stable as possible, never change. But we know that for the play curves, when the play voltage is low, the screen let's say we test this maybe 6L6, and so the play voltage for the curves start from 0 volt. But if we set the HV2 to 250 volt on the screen, it means even when the plate voltage is 0 volt, the screen voltage is still very high at 250 volt. So most of the current, we will see a very high current on the screen electrode, and this high current will cause a voltage drop on HV2. So the trace curves will have more error in the low plate voltage range. So maybe like below 25 volt or so. It's not a huge problem, but it's something to good to know. Okay, here hardware. So basically for every high voltage circuit, we have HV1 and HV2. For each one, we need to change 2 resistors. The one is the current limiting resistor. It's part of the short protection circuit, and the other one is a reference resistor for current measurement. So we need to have both resistors in half, so that we can increase the current capability by 2x, by 2. So here is the circuit of HV1. So R40 is a current sensing resistor. So every time we start a current measurement, the C26, the 45 microfarad capacitor will charge through this path, through Q7, through R48, through this protection diode to the protection fuse to the DUT, and from the ground to the negative terminal of C26. So the current will flow this resistor and give us a voltage. So if we divide the voltage will be sensed by the ADC, and by dividing the voltage by the resistor value, here we have 15 ohms. Then we get the current. So this guy need to be halved. And R48 here is the this guy is a current limiting resistor. Actually, it's a short protection resistor. So when the current flowing through it, increase as the current increase, the voltage drop on this resistor increase. So when the voltage drop is high, it will turn on Q6, and Q6 will immediately turn off, discharge the gate voltage of the switching transistor Q7. So we need to halve the value of this resistor so that it will reach the desired voltage at the 2x current. Okay, so for HV2, the corresponding resistor for is R88 for the current sensing and R96 for the protection circuit. So location of the resistors are marked in red on the PCB, so you can easily find it. So here is R40 and here is R88. These two are current sensing resistors, 15 ohms. Here is R48 and R96. They are these current limiting resistors. Okay, so there are two ways to modify the board. One is you just connect a resistor in parallel with the current resistor with the exact value. So we parallel two resistors with the same value. We effectively halve the resistance. So we can solder those resistors on the back of the PCB like this. So this is an example that we modify R40. So we connect the R40 is 15 ohms. So we connect a 15 ohm resistor on the back of the PCB in parallel with and we need to make sure the body, there is a clearance between the component to the board has a is a minimum of 1 millimeter gap, because for the current sensing resistor it's fine because it works in the low voltage region, but for the current limit resistors, for these two, the potential on it is very high when the transistor is turned on. So we need to make sure there is enough clearance to avoid a discharge path from the high voltage to ground. Okay, so this is a hardware modification required. For software, we also need to change the software to support the 2x current mode. And the support is only available in the alpha version of etracer software. So in other words, once you made the modification to the hardware, you can no longer use the formal release version of software 2.0x. You have to use 2.1x alpha. So there, for the software, there are two places need to be configured. So the series resistance, the HV circuit, and the checkbox of the 2x current operation. So for the series R resistance, we need to subtract the total amount of the resistance we reduced with this modification. So in total we reduced about 12 ohms from the default value of 25 ohms. So we'll need to set this value to 13, as this field only takes integer values. And we also need to check the 2x current checkbox. So here is the one need to be set, configured in the config window in the software. So we need to change this 2 to 13 from 25, and we need to check this checkbox. Okay, so when the status of 2x current measurement checkbox is changed, the software need to be restarted. So the software will pop up a reminder message window to warn the user that the application need to be restarted. Okay, so after the 2x modification, we need to do a full current calibration. For a quick verification, we at least we need to do the DC offset calibration. And it is observed that the curves for DC offset calibration are slightly sloped with the 2x modification. I really don't know the reason because I checked the firmware code, everything should be fixed. So, but I mean, this is not a problem, I think. So here, if we before the 2x modifications, the DC offset current is more or less a horizontal line, but after the 2x mod, we will see a slightly sloped curves. But the software will take care of it. Okay, so here is modification required for the 2x current support. And here I can show you. I'll show you the problem we talked about, which attribute in a different way. So this board here. Sorry, I forgot to describe the second way to modify the board. The second way to modify the board is replace these values, resistor values with the correct value, with the halved values. So for example, for this guy 15 ohm, we need to replace it with a 7.5 ohms resistor, and for this guy 8.2 ohms, we need to replace this guy with 4.1 ohms. But it's probably not easy to find the 4.1 ohms resistor. So so any value between 3.9 to 4.3 ohms should be good enough for the value to replace this guy. Okay, and the resistors are it's quite common. It's a 1/4 watt metal oxide resistor. No, it's metal foil resistor. So you can easily buy them. I don't know, maybe Radio Shack or from online stores like Mouser. Okay, so here is this board. Here, what I have here is a calibrated board. Okay, maybe I show you how to calibrate the board after the modification. So we first connect, then we hit calibration, then we need to remove all wires from the board, reset the scaling. So first of all, we need to do a offset calibration. Okay, so make sure that the board is not connected to anything. So now we can see the DC offset, and you can observe the curves are slightly sloped. Okay, after the offset current calibration, we need to do a gain scaling, current scaling calibration. So for the low current, I have a very precise resistor of 10k ohms, so I'll use this one. And for the high current reference resistor, I have in the box I have a 10 watts resistor, which is not which is 5. I think it's 10% error. And when I measure it, use my Fluke multimeter, the reading I have is 1004 ohms instead of 1000. So we can change this field to reflect this measurement. So now let's connect the HV1 low current scaling. So we need to first we need to calibrate for the low current region. And let's do this. So before we start the calibration, we need to make sure the 2x current measurement and these two fields are changed with the current value, and we hit apply and we restart the software as described in the document. Okay, and now we're ready to do the calibration. So first we need to connect the 10K ohm resistor between HV1 output and ground. Like this, ground, HV1. Okay, and we can hit the calibration button. So in the message window say please connect 10K resistor between HV1 and ground. Click it and wait a moment, and you will get the software will calculate the scaling value. And similarly, we connect the 10K resistor between ground HV2 and ground. Okay, now we need to connect the 1K ohm resistor for high current calibration. Please be very careful, because after this 2x calibration, the calibration voltage is doubled. So in the unmodified for software and hardware, I used 300 volt to calibrate the current, and for this 2x mode, actually the calibration voltage is 600 volt. So it's very high. So you be sure, make sure you are not touching any part of the output pin. Okay. For high current, the measurement will take longer because the software will discharge more, so it need time to recover. So for HV1 and the HV2, apply scaling. Okay, so the calibration is done. So now we can verify the accuracy of the scaling. Accuracy of the measurement. So what we can do is we can maybe let me clear all parameters. Okay, so we can set the x-axis to 300 volt, y left to 300 milliamp, y right to 300 milliamp. Okay, so for scan we can enable HV1. We start from 0 volt and we end at 300 volt with a step of 25 volt, and we need to set power maximum power, and you need to set it to very high because at the high current, and because we expect at 300 volt we are going to test the calibration quality against a 1K resistor. The one we used for current calibration. So with the 1K resistor, we expect to see 600 milliamp at the voltage of 600 volt across the 1K resistor. Okay, and so at 6, so the power, if you calculate the power, it will be quite high. Okay, let's check the calibration quality. Okay, so if you look at the curve, the voltage is actually the current reading is actually very accurate. So at 100 volt, we expect to see 100 milliamp. So you can see the curves cross the junction of the checkbox of it's right on the grid, so it's very accurate. But however, if you do the same thing on HV2, the story is slightly different. So let's keep the HV1 curve, and we enable HV2 link HV1 run. Okay, so as you can see, at the very low output current, the HV2 current is actually very close to HV1 current, but at the higher current, the current reading will be lower compared to the HV1 curve. And why is that? It's because the x-axis we use is HV1, and here HV1 is not connected to everything, so the capacitor is not charging, does not discharge much current on HV1, but on HV2 the capacitor is heavily discharged at the high current region. So that's why when we use HV1, the voltage on HV1 to plot the HV2 current, we'll see this phenomenon. But if you read the CSV, the output file has a HV2 voltage. So if you plot the curves using the data file in the the CSV data file, you can eliminate this problem. So this problem for etracer, I think it's also only significant for testing tubes under pentode mode. Okay, so that's it. I hope you enjoy this video, and I think I'll just wait for you guys' feedback. If you guys really want to do this modification, and then I'll try to find a way to make your life easier. I think I can offer a free modification. It's this is not an upgrade. This is just a modification. So I can do the modification for you, but for overseas customers, you probably need to pay the round trip shipping fee. Okay, that's it. Let me know your comment, and have a nice day. I'll see you next time. Bye.